Hi, everyone. Remember when we found possible numbers of turning points for the graph of a polynomial? Well, now we're going to talk about Descartes' rule of signs, which will help us figure out possible numbers of positive real zeros and negative real zeros, accounting for multiplicity. So a double zero counts twice, for example. Okay, first off, let's assume that f of x is a polynomial with real coefficients and written in descending powers, as usual. And remember to factor out the GCF first, if it's not 1. So for example, if you see x cubed plus x squared, make sure you factor out the x squared first, and then you'll deal with x plus 1. This guarantees that we have a non-zero constant term in here, a sub 0. The same went for the rational zero test or rational roots theorem. We need a non-zero constant term in there. And actually, you don't have to worry about missing terms. Now we're going to use this idea of variations in sign. The number of variations in sign in f of x, written in descending powers, is given by the number of sign flips. So instead of the fancier term variations, I might just refer to sign flips. And we're focusing on the non-zero coefficients as they're read from left to right in the descending powers form. So we're going to focus on these variations in sign, or sign flips, in the descending powers form. Let's go straight to our old example. F of x equals 4x cubed minus 5x squared minus 7x plus 2, our old friend. Now, what if we wanted to apply Descartes' rule of signs? What if we didn't know the zeros already? What if we wanted to apply this rule? First of all, we'd want to count the number of variations in sign, the number of sign flips. The number of variations in sign, that is the number of sign flips in this descending powers form. It may be helpful to put a positive sign in front of the 4 because 4 means positive 4. How many sign flips do we have as we read this from left to right? From positive to negative, that's a sign flip or a variation in sign. That's why I put the positive sign in front here. We do not have a sign flip here. We do have a sign flip here from negative to positive. So we have 1, 2 variations in sign. One, 2. So what does that mean? That means that I use a bit too much notation here. This means that the possible number of positive real zeros of f could be, we'll start with 2, which is the number of sign flips, and then count down by 2s. Similarly to the turning points, the number of turning points. Count down by 2s. Stop before you hit negative numbers, because you cannot have a negative number of positive real zeros. So we start with 2. 2 minus 2 is 0. And we stop there because you cannot have negative 2 positive real zeros. So the possible number of positive real zeros of f could be 2, the number of sign flips or variations, or if you count down by 2, it could be none. There could be no positive real zeros. So what are some possibilities in general? What are some examples of polynomial graphs that have 2 or 0 positive real zeros? Okay, so here's our old friend, right? Y equals this over here. It turns out that we are going to have 2 distinct positive real zeros. These correspond to the x-intercepts to the right of the y-axis. We have here 2 distinct positive real zeros, each with multiplicity 1. So that's one possibility. And in fact, we do get 2 positive real zeros, each with multiplicity 1. But in principle, we could have gotten something like this. Y equals the square of x minus 4, for example, where 4 here is a positive real zero of multiplicity 2, and we get a bounce. So remember that we take multiplicity into account. When we say two positive real zeros, we could have two distinct positive real zeros, each with multiplicity 1, or we could have one positive real zero of multiplicity 2. One distinct positive real zero of multiplicity 2. Or it's possible here that we could have no positive real zeros. For example, consider y equals x squared plus 1 in blue here. This thing had no x-intercepts whatsoever. It has no real zeros whatsoever. Now, Descartes' rule of signs doesn't say which number it is, but like with the number of possible numbers of turning points, right? With the possible numbers of turning points, we list the possibilities. There could be two positive real zeros or no positive real zeros. Now, what about the possible number of negative real zeros? Well, like with even and odd functions, what do we do? When we studied even and odd functions, what do we study? We studied f of what? The opposite of x. And this is to find the possible number of negative real zeros. So consider f of opposite x. Every time you see an x in the rule for f of x, replace or substitute with the opposite of x in parentheses. So we get this, and we simplify. We get negative 4x cubed minus 5x squared plus 7x plus 2. This time, we have only one sign flip or sign variation from here to here. So what are the possible number of negative real zeros of f? The possible number of negative real zeros of f could be 1, the number of sign flips we get here. 1 is the number of sign flips or variations we get here. Okay. It could be 1 or, well, we can't go to -1. So actually, Descartes' rule of signs is very informative here. We know that we have to have exactly one distinct negative real zero, and its multiplicity must be 1. Well, look at our red graph over here, right? It was the -1 over here. -1 was the only negative real zero for the function, and it has multiplicity 1. Notice the cut here. Now, bear in mind, what if we had gotten something like 4 variations in sign? Then, like the rule over here, we take that and we keep counting down by 2s, and we stop before we hit negative numbers. So if we had had 4 variations in sign, then we would have counted down to 2, and then to 0, and we would stop there. So if f of opposite x ended up with 4 sign flips or variations, then we could have had 4, 2, or 0 negative real zeros. Again, a double zero would count twice, a triple zero would count 3 times, and so forth. So this may be helpful in conjunction with the rational zero test or rational roots theorem, for example. And again, sometimes Descartes' rule of signs will say that you have exactly 1 or exactly 0 positive or negative real zeros. Sometimes we get lucky and we get strong information like this. Okay. Now, part I on upper and lower bound rules, I'm not going to hold you responsible for this, but it is in my notes, so you can skim it over. Basically, you can use synthetic division to show that the real zeros of our polynomial must lie in some closed interval. And you put these numbers in the dunk tank, and you analyze the numbers in the third row. But that's an optional portion.